Good evening, fellow researchers. My name is Etienne Dreyer. I'm a doctoral student at Simon Fraser University. And we are going to hear a little bit of the same thing. So if you didn't catch it the first time around, make sure to perk up, and maybe this time you'll get it. So actually, Elham and I do work on the same analysis, and our approaches are complementary. So so without need to explain this again, we're looking for a new particle called the Z-prime boson, using the Atlas detector to look for this. The statistical perspective is a little bit tricky because I know it's a bit of a sensitive topic if you're not very fond of statistics, but bear with me. Let's get started right with the background. The Atlas detector, we've heard a little bit about this tonight. I like to think of it as a 100 megapixel camera, except that it weighs as much as the Eiffel Tower. And it's trying to keep track of about 1 billion proton-proton collisions per second. So this is truly an amazing machine. What about the Z-prime boson? Well, I hope you're convinced that the standard model is accurate, but not complete in its description of nature. And many of the theories which are taking us beyond the standard model in terms of describing nature involve new gauge particles, many of which we call a Z-prime boson. It's a bit of a generic term for a particle which will be similar to the electroweak Z boson, so the regular one we know and love, just heavier. So it will have a very simple creation and decay process that we're looking for, where these are quarks that come from the initial colliding protons, and we look for the final state, which is 2 electrons or 2 muons. We call those both leptons, right? So this is a dilepton final state. If the Z prime exists, then it should create an excess in the number of lepton pairs that we measure with Atlas, right? And because it's an unstable particle, the energy of those lepton pairs will be clustered around the mass of the Z prime boson. So how do we hunt for the Z prime in Atlas? If it was the only thing that produced dilepton final states, we'd be done. We would just need to find one. Of course, there are tons of processes that produce dilepton final states. The most important one here is Drell-Yan. So you can see these are actually the 3 dominant processes shown in increase in cross-section. What's important here is that each of these has 2 leptons in the final state. So these are also contributing, and these form a background. In order to look for the Z prime, then we need to simulate the background events, to simulate the background processes, to know how many lepton pairs we expect as a function of the invariant mass of the 2 leptons. And then we're going to compare it to what we actually count in Atlas. That's exactly what you see here. So these black data points are simply counts of dilepton final states binned according to the energy of those 2 leptons. The invariant mass, as Elham described well. Now these colorful things here, histograms, are all stacked together, and those represent the contributions from those background processes. As you can see, when you add them up, we get a qualitative agreement between the data and the Monte Carlo. So it doesn't look like a signal, at least not by eye. But how can we be a little more quantitative about this? How do we search for a signal using a statistical framework? Imagine if in 2017 we had something like this. Now, don't get me wrong, this is again just a toy, a pseudo data set, and I've just for fun injected a signal at 3 TeV. So this is what I mean when I say it should produce an excess. The first question we need to answer is, what's the likelihood of getting these data under the background only versus the background plus signal hypotheses? The likelihood is simply a product of Poisson probabilities in the bins across the data set, where the expected number of events in each bin depends on the hypothesis you're testing, of course. If you're testing the background-only hypothesis, you expect, say, BI number of events. If you're testing the background plus signal hypothesis, now you expect to have some signal events multiplied by this parameter we call the signal strength, which essentially modulates the peak, the contribution from the signal. So we find the maximum likelihood under both hypotheses by fitting the data with templates, basically expectations for what the background and signal should look like. Here's the di-electron background template. This is essentially what you saw before on the money plot. This is just telling us for each of these invariant masses, how many events do we expect from the background processes? Similarly, we can simulate how a Z prime boson should decay and what that shape should look like. What we can't predict is what its mass is. So here I have actually a few different hypotheses for what the mass might be. And we're going to test all of these and see if any of them show up in the data. Essentially, then the data is either, can be described in two ways. You can think of it as a background-only process or a background plus signal process. And each of these two alternatives gives rise to a different value for the likelihood. Let's say we do this test, and we, of course, find some discrepancy between the two models. How do we quantify, or how do we evaluate that difference? The Neiman-Pearson lemma actually tells us that the optimal way to distinguish between these hypotheses is to construct what we call a test statistic, a discriminator, if you will. And this is called the log likelihood ratio for obvious reasons. We simply take those two log likelihoods and put them into this format. Now, if we have an excess of events, that means we've counted more than we expect from the background. And that's actually, by this construct, going to give us a positive value for the Q value. If we see just as many as we expect, we're going to get Q0 equals 0. So now you kind of see how this thing rolls. If we see less events than we expect from the background, we call that a deficit, and the Q0 is negative. The Q value kind of tells us the signal presence at the point that we tested. However, we all know that data fluctuate. So we have to answer the question, what are the odds that the observed Q0, Q value, let's call it Q0 hat, what are the odds that it's just a background fluctuation? The answer to that question is the p-value. So this is the probability that under the background-only hypothesis, you would measure a Q value larger or equal to the one that you saw in data. Essentially, the chances that you got fooled. Now, one way to get at this is to just generate many background-only pseudo-experiments and see how many of them do this. How many should we expect actually have big fluctuations like this? Thankfully, this guy Wilkes told us what the shape of that distribution should be. It should follow a chi-squared distribution asymptotically. And so, as I described, the p-value would then be an integral on the tail of that distribution, including the extreme values. P-value is a probability. And so it's handy to quote it in Gaussian significance. And this is what people are talking about the Z value, which you often hear in terms of 3 sigma or 5 sigma. So to quickly summarize this, we have our data set. From that, we calculate these likelihood under both hypotheses. That we wrap together into the log likelihood test statistic, which then allows us to get the p-value. And that's what I've plotted here. You can see it responding nicely to the signal that I injected, can't you? This would be very exciting. This is kind of what I would like for my thesis. I need to talk about a phenomenon called the look elsewhere effect. Now, since I mentioned we don't know the Z prime mass, we need to test various different locations. We need to test different hypotheses and see where's the largest excess. And that's what we see here. Again, 5 sigma here in this toy experiment. That would constitute discovery in high energy physics. But the fact that we've looked at so many different spots means we've increased the odds of seeing a background-only fluctuation. This is called the look elsewhere effect, and Elham actually talked about this as well. It essentially is drawing attention to these sorts of fluctuations which came from no background. So the global p-value is then the thing that we need to quote because it compensates for the look elsewhere effect by giving you the probability of observing a fluctuation at least as significant as the one we observed in data, but the probability of observing that under the background-only hypothesis anywhere in the mass scan. Okay, maybe that is kind of a big little paragraph here, but this essentially is reducing our confidence in the discovery by incorporating the fact that we've looked at so many different tests. So again, we can generate this by simply throwing many different pseudo-experiments under the background-only hypothesis and then calculate the p-value by brute force. For each of these pseudo-experiments, we would go and do the whole scan and see where's the most significant point. And we would add it to this distribution. You see that here out of 50,000 toys, we do have a handful that had up to 5 sigma fluctuations. Then the global p-value corresponding to an observation of, say, 4.2 sigma or so would simply be this integral divided by the total sum. Okay, what you see here is a quantification of the look elsewhere effect. Essentially, it tells us that if I go to my data and I see a local significance of 5 sigma, because of the look elsewhere effect, I actually need to quote 4 sigma because of the fact that you've looked in a range of masses and you might have seen a fluctuation. Let me quickly blaze through the latest search results using this method. In the dielectron channel, of course, we are looking at the possibility that the Z prime is decayed to 2 electrons. And now we have again the same p-value scan, but now not on a toy, on the actual data. So here the most significant point is where the p-value is lowest, corresponding to just almost 1 sigma global significance. In the dimuon channel, similarly, we can see that there are not very significant excesses here. In summary, I've told you that we're looking for a localized excess of dilepton final states in Atlas caused by a hypothetical Z prime boson. Now, we also talked about how we can distinguish between the background only and background plus signal hypotheses. And I talked about the log likelihood ratio. This is, again, the optimal test statistic for discriminating between these two hypotheses. We also talked about the look elsewhere effect and how the global p-value of an observed excess is the probability that the background would produce a fluctuation anywhere in the mass range that's as significant or more significant than the one that you report from data. Now, as you saw in the previous 2 plots, unfortunately we don't have any signal observed. And by the way, those plots were from this conference, ICHEP, last year in August. We are currently sitting at 36.5 inverse femtobarn. And that's much larger than the 13.3 that I showed you there. So I can't release those results yet, but we're still actively searching and hoping that perhaps this is a path towards new physics. I appreciate your time, and I'm looking forward to your questions.
Do we expect anything from Orion on this?
We'll see. It's been tricky.
Could you go back to the, I think it was the penultimate slide just before summary?
Yes.
So you have a less than 0 sigma significance. So that's remarkably remarkable. What does that even mean?
You've expressed it very well by saying that. It's remarkably unremarkable. So what the global significance kind of encapsulates is the likelihood of, not the likelihood maybe, but the tendency of the background to produce signals all over the place in this, produce fake signals, of course, all over the place. So what it means if you have a negative global significance is that typically the background will produce some significant excess, some significant fluctuation in this range. But when we came to the data, we didn't even see one of those. So actually, the data is more background-like than we typically expect, even in statistical fluctuations. Thankfully, it's not too far off. So we're getting close to 0 sigma here. But it's a good point. Remarkably unremarkable.
Being fair.
Thank you.
Being fair.
Well, the fact that you have a line that goes close to 0 tells you that that's what's happening.
Yes. Yes, it wouldn't be a disaster if it wasn't. But again, yeah, this is kind of could be that fluctuation, which is yeah, good observation.